My name is Janita Jung. I am the lead of the Young Professionals portfolio on the UQ Young Alumni Board. And it's wonderful to see so many of you here. I know it's the end of the year and everyone's busy, so thank you so much for coming and joining us tonight. And those tuning in online as well, thank you for joining us. Before we begin, I'd like to acknowledge the traditional owners and their custodians on which we meet. Sorry, I'm just trying to, there we go. Yes, I'd like to acknowledge the traditional owners and their custodianships of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country, and we recognize their valuable contributions to Australian and global society. So thank you. For those who may not be familiar, the UQ Young Alumni Board is a group of dedicated volunteers who work closely with the university to foster a sense of community among UQ's young graduates. Our Young Professionals portfolio in particular focuses on hosting events like this one, where learning, inspiration, and connection come together. Tonight, we're showcasing 5 remarkable UQ researchers whose work is pushing the limits of what's possible, innovations that could shape the way we work, live, and play for generations to come. From snake venom gels that stop bleeding to robotic exoskeletons for motor neuron disease to AI, neuroscience, and hypersonic materials, these breakthroughs demonstrate the incredible impact UQ research continues to have on the world. So yes, we invite you to relax, enjoy your food and drinks, and get ready to explore what lies beyond the boundaries. It's now my pleasure to introduce our first speaker for the evening. Dr. Amanda Kijas is a senior research fellow at the UQ Center for Clinical Research, where she leads innovative work at the intersection of material science and biomedical research. Her current project, developed in collaboration with the U.S. Department of Defense, uses proteins from snake venom to create a first aid gel that rapidly halts critical bleeding, a life-saving solution with potential to transform emergency medicine and trauma care worldwide. Please join me in welcoming Dr. Amanda Kijas.
Yeah, so I'm a Motor Accident Insurance Commission fellow, and I'm really interested in biomedical research. I lead a program based on wound healing, from developing point of injury bleeding control agents, which I'm going to speak to today, to engineering new materials for regenerative healing. And that's looking at underlying mechanisms where we can understand how these processes are happening in our bodies, to developing new prototypes and engineering those, to then doing preclinical evaluations where I work closely with clinical researchers and medical professionals who have expertise beyond my lab-based experience. So I'm just going to warn you that the next slide is maybe a little bit sensitive for some people, and those who don't like to see wounds or blood might want to look away for the next minute. The reason why I'm showing this is because these aren't made in Hollywood. These are real wounds from real patients with real clinical need. And we can do better in this space. I can tell you that these patients aren't having a quality of life that we would ideally have. And we don't have the innovation in this space yet to help these patients. There's still huge shortfalls in developing better and more improved products, from chronic wounds that I'm showing there to bleeding control agents. So for those who are less sensitive, we can come back and that'll be the last time I show those kind of horrific images that even kind of upset me. But what that does is drive me, and that gives me the passion to kind of really come up with better solutions. So I'm going to give a bit of background, because I'm going to talk today about point of injury bleeding control products, and about how our blood functions in a normal situation to deliver oxygen, provide us with those nutrients, and remove waste products. And as we've all probably done in the kitchen, cut ourselves with a knife, and within a minute, hopefully, we can hold our finger and it will stop bleeding. But things can become dysregulated, and that balance between that fluid blood that delivers all those nutrients and things to a blood clot can be problematic or delayed after major trauma. And when those things do fail in our bodies, which are so perfected and optimized, we can have uncontrolled bleeding. And what I'm showing here is in a civilian setting where after major trauma, deaths due to uncontrolled bleeding is significant. That's because we don't have products to address this effectively. In a military setting, so this is US Department of Defense numbers, it's up to 90%. And these are potentially survivable injuries. So we're not talking about something so severe, but there are not products good enough to control that bleeding. And interestingly, most of these in both the civilian and military settings are deaths that are occurring before these people are getting to hospital. So we're needing these point of injury, these point of care kind of products. And often they're in the softer tissues where we can't apply pressure, and I'll come to that now. So as I said, I'm a Motor Accident Insurance Commission Research Fellow. And so there's really high rates of deaths associated with road accidents. And these are mainly deaths occurring most prevalently in our youth, so between 0 and 29 years. And in Australia, it's the leading cause of traumatic injury in Australia. And you can imagine that in our geographically kind of diverse and sparse kind of country, especially in the state of Queensland, there's huge delays to get to hospital. So we're talking up to 1.4 hours in Australia to get to hospital after injury. This is significant, as you can imagine, if you've got extreme traumatic injuries. So that role of a first responder or bystander, whether you're someone on the road who pulls up after a road accident has occurred, your role is pivotal, and those very first steps that occur to save that person's life potentially are key. So actually, uncontrolled bleeding is actually the world's leading cause of preventable death. And it comes back to what I was saying, is that if these people had a product to control their bleeding, they would survive. And this is what drives me, is that we can do better. And you can bleed to death within about 5 minutes, depending on your injury and your arterial problems. And this was such a big impact that in the US, a group of clinicians actually formed an organisation called Stop the Bleed. And what that was just basically to teach how to control bleeding, to apply pressure, to wound pack, apply a tourniquet, very basic first aid, where addressing bleeding had been overlooked in generic kind of first aid training. There's now an Australian arm of this called Stop the Bleed, and their whole kind of process is to teach first aid techniques to control bleeding. So I want to circle back to where we're at and where you might be at one day driving the rural roads of Queensland, where if you're a bystander, you're going to go, hopefully you have a first aid kit in your car and you'll have a variety of things in that first aid kit. You will hopefully have something that you might be able to use as a tourniquet. A tourniquet is one of the most effective ways to control extremity-based bleeding. And they've been around for a long time, hundreds of years. Not very much innovation in that space. There's been some innovation by US Department of Defense to be able to apply them with a single hand. Otherwise, you have gauze in your first aid kit. To tell you the truth, this is actually highly effective at controlling bleeding compared to really high-end things like Quick Clot Combat Gauze, which is a first-line bleeding control dressing that the US military use, Queensland paramedics use. Definitely is effective, but your gauze is just about as effective. In the trials that were done to compare gauze to Quick Clot Combat Gauze, the Quick Clot Combat Gauze did not reduce bleeding. It did show a slight improvement in survival. So we're talking about a highly effective thing in your first aid kit. It's been around for 4,000 years. Not much innovation has actually progressed. So we can do better here. And that's where we came up with an idea to kind of look at natural sources of potent and specific molecules from the venomous snake. And there we've developed a snake venom gel to try and control bleeding at point of injury. So snake venom, like many venoms, is a really complex mixture of molecules. They're really potent, all playing slightly different roles. And we know that a bite from the eastern brown, which is a local Australian snake, can kill people or have extreme negative outcomes. But we've taken two molecules from two of the most venomous snakes in the world. You've got the saw-scaled viper on the right there and the eastern brown on the left. One of those molecules from the saw-scaled viper can accelerate your natural clotting system. So it doesn't replace it, it accelerates it really fast, called eccrine. The other molecule we've taken is from the eastern brown. And what that does is stops your blood clot from breaking down again. So the two reasons you might bleed to death is you can't form a clot for various reasons, physiological or medication, genetic, or that blood clot breaks down again too fast. So these two key things, and no point of injury product currently addresses both those arms of why people bleed to death at point of injury. So this is where another innovative step has come. And basically, if I jump to where we're at with this product, is that we've used those two molecules in the context of a gel at the moment, where we're exploring other delivery scaffolds where no injury is the same. And what we did with this product is we looked at two key parameters for effectiveness of a bleeding control agent. One, to reduce blood loss, the other to reduce the time of bleeding. And what we found in our evaluations is when you have a functional coagulation system, so this isn't always the case after traumatic injury, your body's natural systems become dysregulated. So when it's functional, you have your clotting taking about 11 minutes after this particular injury and up to 22% total blood loss volume. That's actually still quite significant and you would be quite unwell. With our venom gel, we were able to reduce that to 3.9% blood loss and clotting at less than 3 minutes. We couldn't evaluate shorter times than that. But the key thing that I want to highlight here is a dysfunctional process. So this product was equally effective when those clotting systems are going to fail, which mimics better that traumatic situation. And in this model, the animals would have uncontrolled bleeding. So they couldn't clot their blood and they would bleed to death. But our venom gel was able to still control that blood loss at still less than our natural body system to clot blood, and again at less than 3 minutes. So we're really excited by this, and it's now progressing further into preclinical space with collaborators like Professor Mark Midwinter. And we're hoping that this, as it keeps going, where we keep seeing really positive outcomes from this kind of agent, we're kind of pushing with extra funding and further research to go more into preclinical, and we hope one day to be a product that we will be putting in people's first aid kits. I want to acknowledge Professor Alan Rowan and his broader group, past and present, and particularly now Dr. Ram Yegapan, who did his PhD on this project and progressed a lot of this work. And the rest of the collaborators who have played all instrumental roles in progressing this project where nothing happens in isolation. It's big teams, big money that comes together to make this work. And I especially highlight the Australian Red Cross Lifeblood, who supply us with blood to do all these fundamental evaluations where we can't do very much without those resources. And all our various funding that has been really generous to support this and progress it to where it is today. Thank you, and I'll take any questions now, or I'm really happy to chat later if needed.
Wonderful. Thank you so much for that presentation. I'll help moderate the Q&A. But yes, sorry, I think there was a bit of a round of applause happening. Can I interrupt you? So if you do have any questions and you're here, please just raise your hand and I'll come around with the microphone. Or we do have Slido as well. If you go to slido.com and type in UQ alumni, you can ask questions. We do have one. I'll start off over here into it already. One moment. Oh, okay. Yeah, I've got those up as well.
How sensitive is the gel to like temperature, humidity? Just looking back to that 90% fatality rate in the military, I'm just thinking about the conditions that they would face.
That's exactly right. And so the US Department of Defense are really nice because they publish all their requirements for these kind of things because they're really austere environments. They're extreme temperatures, cold, hot, and all this. And this gel, as it was originally published in the paper that I'm showing, wouldn't be suitable. We're now doing a dried formulation and other scaffolds. So gauze is still an incredibly powerful material because it's got a physical strength. So you have all different kinds of bleeding. So gauzes has physical strength, so we can activate those clotting pathways and things, but this has a stability and a strength that no gel will ever have. And this is about different kinds of bleeding and injuries that they all have different needs. The gel was actually because a lot of those deaths are actually related to non-compressible wounds. So these aren't where you can put a tourniquet on or apply pressure. You can, but in the soft tissues and junctional wounds, it's extremely hard and they're called non-compressible wounds. So a gel can go over that and coat it. But yeah, there's with any injury or medical problem, there's a huge complexity of what you're trying to address, and each of them have a place. So a gel does have a place, especially in the intracavity injuries where you don't want to be applying pressure to soft tissues. But you're right, it's not going to be in a combat troops pack like that, but a dried formulation where these venom proteins, something else that's really great about venom is they're extremely stable proteins. They're structurally kind of fixed, so they're not flopping around, and so they're very stable. So you're right. Yep, stability is a huge thing, but we have some kind of lines of progress that are going down that line.
Thank you for that question. We have another one here from Dwight Walker. He says, can you use artificial blood when there is blood loss?
Can you
use artificial blood when there is blood loss?
Yeah, so artificial blood is a huge thing. And I was just speaking to some people from Red Cross Lifeblood, and they have a huge drive to create synthetic blood. And there's huge research in that space because currently a lot of clinicians, so if you make it to hospital, the first thing they would do is transfuse you to restore your blood as much as possible. But there's shortages always. And in military situations, it's a different kind of extreme situation, especially if you're serving in the kind of field. So definitely synthetic bloods, and they're coming platelets, which are a key cell type in our blood that helps us make a strong clot, which is fundamentally important, is also key. And there's definitely, it's not my space, but I know there's actually UQ researchers and researchers in Australia working in that space, and definitely equally important because we won't always be able to control that bleeding.
Okay, thank you. A question here up front.
I was wondering with the gel, how is it implemented? So like in the picture, is it kind of injected into the wound to kind of help? And then also talking about with the gauze, is there a way to sort of cover the gauze in the gel and then it would have like possibly a double effect?
So you're doing our work for us. Yep. Definitely. So the gel, as I said, was these non-compressible wounds in the soft tissue. So the idea was to inject it into the intracavity space and control that bleeding. Even if you're at a clinician's hand or a medical person, they can't always see where the bleeding is. So just injecting it into a space where the bleeding's coming from would hopefully work. And that's where that originally kind of was pushing. But you're exactly right. That's what we're actually doing at the moment, is trying to do a combination where a gel has advantages, but it doesn't have physical strength. So definitely that's a space we're looking at, and gauzes are very stable and really effective hemostatic dressings.
Wonderful, thank you. Couple more questions. What has the collaboration process been like with the U.S. Department of Defense? How important are these kinds of partnerships in advancing medical innovation?
So it's quite interesting. So funding in Australia for medical research is what it is, but we had really preliminary. So back 7 years ago, when I first started on this project, I'd been working on it for about a year. I had really preliminary data, just blood clotting data from Red Cross blood in a clinical machine that we can measure clot formation and breakdown. And we pitched the project to the US Department of Defense, who have invested a lot of money into medical research, especially with regard combat casualty care. Huge money they'll put into support the health of their combats. And we actually got that grant, and it was a less than 2% success rate on really, in Australia, I don't think we would ever have in a million years got a grant based on the preliminary data and, you know, the kind of state. Yeah, so it was less than 2% success rate, and that's how we got that funding to kickstart. And they've been very supportive, and we got follow-on funding to continue that project to a more dried formulation to address those kind of things. But yeah, they've been really fundamental to this project, and we've now got a lot of Australian funding as well. But that very early preliminary research, you know, would have been hard to find here in Australia for medical research.
Lovely, thank you. I think we have time for one more question here. What initially inspired you and your team to explore snake venom as the basis for a bleeding control agent?
Yeah, well, that actually
did.
comes from Emeritus Professor Martin Lavin, who actually has worked on this space for a long time, and he started very much at the fundamental things of taking the venom from the eastern brown and various other Australian snakes, taking different fractions and looking at the components and the effect on blood clotting, blood formation, on all these different aspects. And by isolating individual proteins from the venom, he was doing really more fundamental research and identified, so one of those molecules, textillinin, I spoke about to stop the blood clot from breaking down, he identified very early on in his research from his team, which was quite a broad team as well, who have contributed to that work to get to this point. And yeah, so that's how it kind of started. And then eccrine, the other protein that accelerates clotting, has actually been used in clinical space more for blood measuring of clotting, but no one had ever put it as a concept to put it inside a body or to use it as a bleeding control agent. So it's that's not a new molecule, and people have been using it in the clinical space for clotting assays, blood clotting assays. If you're a clinician, you might have heard of it, but not as a bleeding control agent. So yeah, that's where the two molecules came from.
Wonderful, thank you so much. Any other questions from the room? Otherwise, I think we'll proceed to our next speaker. Lovely, thank you so much, Dr. Kuta. All right. Next up, it is my pleasure to introduce Associate Professor Michael Heinzman, the Center Director of the Center for Advanced Materials Processing and Manufacturing and a senior academic in UQ's School of Mechanical and Mining Engineering. Michael leads one of Australia's largest composite materials research groups, connecting more than 60 researchers and 110 PhD students across industry and academia. His work focuses on advanced composite materials and manufacturing processes, bridging cutting-edge research with real-world applications. His team's innovations from wear-resistant components for coal seam gas operations to ceramic matrix composites for hypersonic defense technologies exemplify this impact. Ooh, that's a big sentence. A trusted collaborator with global industry partners such as Lockheed Martin and Thales, Michael continues to champion innovation that strengthens Australia's materials science capability. Please join me in welcoming Associate Professor Michael Heinzman. Thank you.
All right, I think you have to thank ChatGPT for a lot of that wonderful wording. So I try to keep it a lot simpler. I've used a lot of pictures and a couple of videos to hopefully find a good balance between addressing and maybe even giving some knowledge to the engineering alumni that we have, but also making it interesting for people that maybe that do not have an engineering background. So I focus my talk around really, I guess, taking that theme beyond the boundaries and really looking at the work we're doing in pushing boundaries of high temperature ceramic matrix composites. Before I do that, I just quickly wanted to introduce sort of my broader group. So in a nutshell, my group is really focused on trying to put materials into extreme environments. And I never really realized that, but I think it's of the story of my life. I think there's something in me that I think has as of the desire to push boundaries. I think the older that I get, the more I have to move into the water space because it just hurts a little bit less. But I think the same way, I think the work we're doing on the research side is really there, trying to take materials that we've known for quite some times and figure out how you can manufacture them so they're relevant in industrial sense and can fulfill requirements in some of the really extreme environments that you see, whether it's being in defense and space, coal seam gas, or renewable energy in the ocean. So we really deal with all these different domains. Now, when it comes to high temperature materials, I guess the first question is, why do we need them? And probably the ones of you that have done some sciencey type degree would maybe remember this. So there's a thermodynamic concept which is called the Carnot cycle, which basically states that the efficiency of a process, all other things remaining the same, improves when you increase the temperature. And as you know, we're sort of in a phase where, as humanity, we're striving to increase our efficiency to hopefully, I guess, reverse some of the impact we're having on the planet. And therefore, being able to increase efficiency is incredibly important across a huge range of different applications, including turbines. So a lot of the new generation jet turbines starting to use some of these materials for that very reason. And then the other area which is, I guess, really relevant to this talk and focused on some of the applications that we are dealing with is, I think as humans, we always had the desire to fly faster and fly higher. And really that area of hypersonic flight is probably in the aerospace sciences one of the last frontiers that we haven't managed to really overcome. And a critical aspect of that are high temperature materials. Now, when it comes to these high temperature materials, particularly for hypersonic flight, there are a number of requirements which are not easy to meet. So these materials have to resist temperatures somewhere between 1,000 and about 2,500 degrees C. Ideally, they're very lightweight. They have low thermal expansion, so as you heat them up, they ideally don't grow too much because otherwise it becomes really hard to engineer with them. They should be failure tolerant. They should be able to be made in complex shapes, robust supply chain, so you can easy source it, and obviously easy to manufacture, and then they should be ideally very low cost. And the situation is there are huge trade-offs. So there are materials that can do one of those things really good, but all these things combined is very, very tricky. And I guess that's the space that we are trying to navigate. And as I mentioned, today's talk is really so focused on hypersonic applications, and at least the example I picked. But that is to say that there's a whole heap of other areas that you know, in the long run, I think we will see more and more of these materials being used. So I think that will be key for some nuclear fusion type processes, engine technologies of various types, and then various types of energy generation and storage as well. Now, just a little bit of an introduction. So the materials I talk about today are called ceramic matrix composites. And so if the title gives it away, so these are materials that consist of a ceramic and a fiber. So the composite part obviously is the fiber, and the idea is that you combine two materials that have very different properties, and you end up with something that is a little bit better than the sum. Now, to put it in sort of layman's term, to give you the perspective where these materials sit or why they're special, if you look at other material groups that we have, so your metals, the issues with metals are that they're very dense, so they're typically very heavy. Most metals start to soften at the temperature ranges that I talked about, and if they don't soften, they're very heavy. Then the thermal expansion is very large as well, which causes some problems. We then have the ceramics, and most of you that have smashed some plates would be aware of one of the limitations of ceramics. So ceramics are very brittle, but they definitely do have the high temperature resistance, and that's why we really use them as part of our composite. And then obviously you have your polymers. They're very light, cheap, easy to manufacture, but obviously they melt at least, or starting to melt typically at around 200 degrees, and 500 degrees is definitely the end of it. So that's really the idea with ceramic matrix composites, that we combine reinforcing fibers and the high heat resistance of the fibers, and that allows us to make a material that can be engineered to at least meet some of those requirements. So just to sort of explain a little bit what our research niche is. So currently we're the only group in Australia that can make some of these materials, and we're responsible to bring some of that technology to Australia. We're now working with industry to disseminate some of that manufacturing knowledge. But our niche is really in that triangle between materials, manufacturing, and design. So playing devil's advocate, the materials that we're using, there's nothing new about them. People have known that they're good materials for the last 20 years, which in materials terms is still relatively new, but they have been around. Where really the novelty is coming in is sort of figuring out how we can take these materials, process them in an efficient way, but then also trying to design applications that are really out there. So flying at multiple times supersonic speed, so 5 to 10 times faster than the speed of sound. So to give you an idea, that would be, I think, flying from here to the UK in about 2 hours. So very rapid flight. Designing materials for these applications that we can't produce on the ground, that is incredibly expensive to test, is really, really difficult. So sort of navigating this space is sort of our big challenge that we are working on. The process, and we're getting a little bit maybe into the weeds, but the process that we're really focused on is called reactive melt infiltration. And it sounds really simple in concept. It's a little bit more difficult in practice. But the idea is basically that we make a fiber reinforced plastic. We then convert the plastic into carbon. So we end up basically with a material that resembles a little bit of a sponge, which has reinforcing fibers in there. And then we basically fill this sponge with a molten refractory metalloid, so silicon, zirconium, these type of materials. And what happens then is that the refractory alloy reacts with the carbon and forms a carbide. And for the ones of you that have done material science, so carbides, when it comes to sort of thermal resistance, hardness, sit at the very pinnacle of what humans can do with materials. And that's quite an efficient process to make these materials, but the devil is really in the detail, in that we need to really control the microstructure of it, and producing real things can be quite challenging. So here is of one of the applications and projects that we're working on. Hypersonics Launch System is the company, Brisbane-based UQ spin-off. It was in the news yesterday, Channel 9. They're doing incredibly well, really leading the way, managed to raise, I think, $50 million on top of another 100 or 200 million from other sources. So really good success story, and it's a real privilege to work with them on basically sort of solving the problems they really stuck with, which is the most heat loaded parts on their vehicle is where basically the air enters the engine inlet. So there's like a little V section there. So that's where all the air gets forced in. And this part gets incredibly hot. So we're talking, even for short flights, 1,700 degree plus. And basically in this project, we really started from developing the requirements, working with their team, doing some very high fidelity simulation to actually figure out how you fit that part, how you manage the thermal expansion, because their whole vehicle actually gets 5 centimeters longer as it flies because it's heating up. And so there's a lot of challenges to actually make sure that that part stays there, that it doesn't get crushed or it doesn't fall out. Sorry. And then comes the material testing. And again, as I mentioned, we're talking about very big temperature ranges. So we have to figure out how we test these materials to see that they withstand those temperature, but also having all the engineering data that allows us to, for example, calculate thermal conductivity and then use that in the design. And that's sort of one of the specialities and niches, I guess, that we are in. To show you this, how that looks, I've got a little video. So for the ones of you that are familiar with oxytorch cutting, so when this is a torch that you use for metal cutting. Typically, you can cut within seconds through 25mm steel plates. Keep that in mind when you see this video, if it does play. Oops. So that's just a little bit of setup to make sure it's right. So the flame temperature there is about 2,500 to 3,000 degrees C. So by now you probably would have burned a hole through a 40mm or 50mm steel plate. And yeah, so the really impressive thing is, so these materials at these conditions lose less than a milligram of weight over about 2 minutes of these very extreme conditions. Oops. And then the other fascinating thing, and that's really from a material science point of view, is that we sort of that we're connecting from across multiple scales. So for these materials to really work, we really need to understand the microstructure. So what you see here are micro CT, so X-ray images that we then reconstruct the microstructure. So you see the fibers, you see the infiltrated matrix, and then we also see, so the purple bit is the unreacted silicon. And that's sort of the exciting bit. So that's sort of the things material scientists are really excited, and I guess the engineers are really excited about the applications. And then the last bit of it is obviously, once we figured out how you make these complex components, is to do some testing. We extensively use 3D scanning techniques to manage shape tolerances, all the way to now the integration into the engine. And I think, to me at least, it's a little bit of a career highlight, in the sense that so Hypersonics will fly this vehicle sometimes in the new year, and our part will be in the most critically loaded component. And I think even in the history of ceramic matrix composite parts, outside of NASA and some very small unique groups, there hasn't really been that much done to that level. All right, and so that's a little bit stuck with the maybe just a little bit the outlook and a little bit of advertising. So we were, or I was recently successful leading the IRC hub for mass manufacturing of high temperature composites. So that's basically taking these materials, working with industry to figure out how we can make them cheaper, more robust supply chains in Australia. And that's a 5-year effort in the tune of about $15 million. and that we're now just embarking. And I think that really provides some really exciting opportunities that I'm particularly interested in to take it beyond the defense space. So looking at mass manufacturing in Australia around thermoplastic processing, looking at recycling, the circular economy, but also sort of helping our industry to get to a new level of automation, because I think otherwise we just won't be competitive. All right. So very happy to take questions.
Thank you so much, Michael. Yes, if any questions in the room, please do put your hand up. Happy to.
Yep.
Lovely.
Thank you. So I'm not sure if you covered it in the presentation. I'm not from a science background as such, but so with the materials that you mentioned, so when you combine them in the matrix, how do you amplify the positive aspects of each material while reducing the liabilities of the materials? So like, for example, when you're saying about the polymer material, how it has a lower heat resistance, when in the combined material, does that liability affect the full material in its product?
Yeah. No. So that's a really good question, and maybe some of the finer details we have to talk offline. But so the idea is really in a ceramic matrix composite, the ceramic really brings the high thermal resistance, but the biggest drawback of the ceramic is that it has very little resistance to the growth of cracks. So as you know, if you drop a plate, it just shatters into a million pieces, and that's really fundamentally the resistance of crack or fracture toughness that is lacking. And that's really where the idea of having the fibers comes in. So instead of a crack being able to grow through the entire material very rapidly with little resistance, you basically have that fibrous network which then stops the crack. So you can think of it like similar to the ripstop material that you have in sporting jackets. It's pretty much that principle. Yeah. There's like some really fine details to it, but yeah.
Got the contact details up here if you want to ask them. Have another chat. All right, I've got some more questions coming through online, actually. I've got a question here. Do you see hypersonic flight coming into the commercial space? If so, how long away are we?
Look, I think it depends what you define as commercial being. I think, and that's my personal view, the manned, like, civil flights, like say the example flying to the UK, manned with passenger. I still think we're a long way away. Whether it's 20 or 50 or 100 years, I wouldn't make a guess. But I think commercial, yes, in the sense that things like access to space, rapid deployment of various things, and not just defense. It could be reacting to events that needs observations, or weather events, bushfires, even rescue to a lesser degree. I think that we will see I would say in the next 15 years, maybe. Yeah.
Very interesting. Thank you. Another question here from Dwight Walker from last time. Does this material collapse like carbon fiber hull in submarine? I'm not sure if I'm saying that.
Oh yeah, I mean it's a big topic. Obviously, the ones of you that don't understand the reference. So there was the Titan submarine that has given composites a really bad rap, which I think it was more an engineering problem. But so one of the challenges of composite materials is that their behavior is very anisotropic, meaning that typically they perform a lot better in tension than compression. It's a little bit of, and again, without going too deep into the issue, but with ceramic matrix composites, it's a little bit different in the sense that in a polymer matrix composite, which Titan submarine would have used, you have the polymer, which is really soft and not that stiff, and the fibers, which are really strong and stiff. And that sort of contributes to that buckling issue, whereas in a ceramic matrix composite, the matrix is a stiff or maybe even stiffer than the fiber. So we don't quite see that issue of lack of buckling resistance. But nevertheless, I'm not, maybe my talk was a little bit too pro ceramic matrix composites. There's a lot of challenges when it comes to the mechanics of these materials. Yeah.
Got another technical question here. Does the material deplete over time with high heat?
So the short answer is yes, and the really interesting part to it is, you know, we think of temperatures as basically being gradients, and the really interesting bit with these materials is that their resistance is by no means linear. So I gave that example of nearly no ablation at very extreme conditions. If you increase the temperature by another 400 degrees, which doesn't sound like that much if you're already at 2,500, you fall off a cliff. And that's sort of one of the, unfortunately in that space, there is no free lunch in that the materials that are really heat resistant are the ones that are expensive, difficult to make, all these things. So being able to figure out what is just good enough is a big part, and it gets interesting because you really fall off those cliffs. So the short answer is yes, they definitely deplete, but not in a linear way. So if you pick the right materials, and maybe the turbine blades are a good example. So there are now commercial turbine blades using similar materials that last for tens of thousands of hours. Yeah.
Wonderful. Thank you. Thank you very much, Michael.
Thanks.
I think we might move on to our next speaker. Thank you. And yes, if your questions didn't get answered, that came through Slido. We still do have a chance to chit chat afterwards as well. So please do stick around after our presentations. I'm going to hand over to Rena to introduce our next speaker. Rena is part of our Young Alumni Board as well, also on the Young Professionals portfolio. So thank you, Nina.
Awesome. It's my pleasure to introduce Associate Professor Taylor Dick, a leading researcher and group leader in the School of Biomedical Sciences at the University of Queensland, where she also serves as the School Director of Higher Degree Research. Taylor leads the UQ Neuromuscular Biomechanics Laboratory, where her team explores how the body moves and how understanding movement can improve health, performance, and quality of life. Her research sits at the fascinating intersection of biomechanics, neuromuscular physiology, and bio-inspired assistive technology. After completing her PhD at Simon Fraser University in collaboration with Harvard University's of Concord Field Station, Taylor continued her postdoctoral training in biomedical engineering at the University of North Carolina. There, she combined biomechanics and muscle physiology to study how biorobotic devices influence human movement, work that has shaped how we design wearable technologies to support people with mobility challenges. Since joining UQ, Taylor has built an internationally recognized research program that's both deeply scientific and highly practical. One of her current projects focuses on developing wearable robotic exoskeletons to help people with motor neuron disease move more freely and maintain independence, a perfect example of how her work bridges innovation and compassion. Please join me in welcoming Associate Professor Taylor.
Thanks for that. If I knew you were going to read it out, I wouldn't have made it so long. So apologies, I have to stand. I have one functioning hand. I got in a fight with an anchor winch on a sailboat and clearly lost. So I need to stand close because I don't think I can hold both in the hand at the same time. Anyways, it's nice to see so many faces here. I'm glad that Michael's introduced the term efficiency because it comes up in the context of human movement quite a bit in my talk, but now we're all well versed. So I'm going to discuss no surprise, how we can empower movement in individuals with limited mobility using exoskeletons and really hopefully take them from fact to fiction. And before I start, I'd just like to acknowledge the traditional owners of the lands on which we meet, to pay our respects to their ancestors and their descendants. These are the Turrbal and Yagara people, and acknowledge their valuable contributions to Australian and global society. And so really briefly, I lead a pretty diverse research group that right now, I was counting today, we're more engineers than we are biologists. So a lot of engineers, a lot of computational scientists, a lot of mathematicians, and we sort of have three pillars to what we do. We're really interested in combining in vivo and in silico tools. So what this means is studying tissues as they are in the body, whether it be a human or another animal, and using computational models and simulations. We're interested in links between form and function and understanding how the musculoskeletal system, how the brain a little bit, I'm not a neuroscientist, and how the mechanics of the way we interact with the world integrate, and how we can deal with problems as a result of size in humans and animals, as a result of aging, or in the presence of disease. And then finally, I call myself a bit of a wannabe engineer. I'm not a trained engineer. I did my postdoc in biomedical engineering, and I'm really interested in collaborating with engineers to design, apply, and interrogate how these devices called wearable exoskeletons can augment and restore movement. And that's largely the focus of my talk today. And so I would argue, and hopefully there's not too many neuroscientists in the room, that locomotion is one of our most prized possessions. If an animal cannot move, it won't find any food, it won't find any mates, and its species won't survive. And if humans can't move, we know our quality of life drastically declines. And there's really this subconscious high regard in the value in which we place our locomotory skills. And just think about the terminology of movement that pervades our language of achievement. For example, when we do well, we're going places. Good ideas need to get off the ground. We jump at the chance to try something new. We chase goals, we make leaps of understanding, and when we learn a new task, we need to get up to speed. So movement is fundamental. And so what happens when we lose our locomotory freedom? And one particular population where my group has recently started looking at this is motor neuron disease. And motor neuron disease, for those who don't know, is a progressive disease that affects the nerves, particularly the motor neurons that send the messages between our brain and our spinal cord and our muscles. And these messages are important because they allow us to perform movements such as walking, but also really key functions like swallowing, talking, and breathing. And in motor neuron disease, these nerves start to become damaged, they die, and our muscles start to weaken, and eventually we lose control over them and they waste away. There's no current cure for motor neuron disease. It's highly heterogeneous, and the average life expectancy is 2 to 3 years from diagnosis. And I'll comment that it usually takes between 9 and 12 months for these individuals to get a diagnosis from the first time they see the doctor. And so one thing we know very little about in MND is movement. And that's because the focus has been on a cure for the disease. And there's nothing against this, but I'm a biomechanist, so I'm really interested in movement. And if we can understand how the disease influences movement, then we can develop strategies to improve movement. We can use movement signatures potentially as a biomarker of disease onset, of disease progression, or to monitor the outcomes of clinical trials. So movement matters. And I'm really fortunate at UQ when I arrived for them to support me in creating a gait laboratory. So we have this fancy schmancy treadmill. It might not look like much, but it's a $500,000 treadmill. It's got 2 instrumented belts, so each belt moves independently, and it's got force plates under these belts that measure our ground reaction forces, Newton's laws. When we interact with the ground pushes back on us with equal and opposite forces, and we can measure those and learn a lot about the mechanics of how we interact with the environment. We've got motion capture cameras around the room, so we can monitor the movements of our segments in near real time. And we do things like use ultrasound, so dynamic tools to look under the skin. This is my calf muscle and my Achilles tendon. I'm sort of just doing this type of task, but we can do this during locomotion, and then electromyography. So those are the little electrical signals that our muscles produce when they contract. And ultimately, we typically like to combine these different tools together. And so in thinking about motor neuron disease, this banner is really in the way of this. Is there a way to move it? Yeah. Apologies. So I'll start going. So when we get people in the lab, we often then measure these motions, and then we can make digital representations of them moving in space. And just to give you a bit of an idea of what this looks like, we can do this during tasks. Sorry. And I'm right-handed, so it doesn't help. During tasks like walking. This is an individual who has a much larger locomotor deficit, so they're holding onto the handrail and they are walking, but they're walking quite slowly, or during functional tasks like sitting and standing. So just to give you a little bit of a flavor of the data that we can collect. And so really briefly, what have we learned so far about gait in MND? We've learned, and this was known, so it's not surprising, individuals with motor neuron disease, they walk slower and they take shorter and less frequent steps. But what was really interesting is when we look across the different lower limb joints, being our hip, our knee, and our ankle, we found there was more than a twofold decrease in the push-off power. And so think about your muscles can generate some energy. Think of this as almost like the wattage of your calf muscles. And you can see it substantially. It's about half as large in people with motor neuron disease. And it's also variable between the left and the right legs. And then each one of these squiggly lines is a different participant with motor neuron disease walking. And what you might be able to highlight is none of those curves look the same. And so what this suggests to us is that movement is influenced by motor neuron disease. Not surprising, Taylor, but it varies a lot between people. And the ankle is the most important joint to consider if we want to improve walking function. And so what can we do? Well, enter exoskeletons. And for most of us, and if you Google exoskeleton, the first thing or the definition that you'll see is a skeleton that's on the exterior of an animal, functions to both support the body shape and protect the internal organs. So we might think of a crustacean, a beetle, some sort of insect with an exoskeleton. But the second hit on Google are these wearable devices that support and assist movement to enhance the capabilities of the human body. And I have a picture up there. That's GE, General Electric's Hardyman exoskeleton from the 1970s. And so this was a prototype. Only one limb came to fruition. This was supposed to be this super suit that, enabled the workforce in General Electrics to, be able to manufacture cars much more efficiently, to not rely on major pieces of equipment. It failed because just one of the arms weighed 250 kilograms. It's unreasonable. Enter to today, this is a picture of some of the types of devices that we use in the lab. So this is a particular device called a passive ankle exoskeleton. It has a mechanical clutch and a spring that's tuned to the way we interact with the ground. It has no motors and no batteries. So we've really come a long way with exoskeletons. And they're transforming the way humans move. So we've done work, like I said, using these passive devices to improve walking efficiency. We've used powered devices. So now enter a battery with some controller. In people with post-stroke, so where one side of their body is influenced, to see if we can improve their gait symmetry and improve their efficiency. And we've done some more recent fun studies, well, maybe fun, maybe a bit mean, I'll turn this one off, where we trip people on the treadmill. So we rapidly accelerate the treadmill to simulate a trip or a slip, or we pull the rug out from underneath people's feet and look at how they respond. Because we're really interested in if these devices can improve the stability of movement. And of course, balance. We spend most of our time, believe it or not, balancing, just standing still. And so if these devices can improve the efficiency of balance, that would be fantastic. All right, so getting back to motor neuron disease, what's currently available for people in Australia with motor neuron disease? Well, we've got wheelchairs and scooters, and so when people completely lose their mobility, they typically move to a wheelchair or some sort of motorized scooter, and there's some pretty fancy schmancy wheelchairs and motorized scooters. I won't go into much detail. There's the more passive walking aids when the deficits are low, and there's also ankle-foot orthotic devices, so either for the ankle or for the knee and the ankle, these are dictus bands in the middle. So essentially think of this elastic band that attaches to your shoelaces and keeps your toes from tripping on the ground, which is a really common foot drop issue in people with motor neuron disease. But one problem with all of these aids is they're passive. They don't adapt to the person wearing them. They don't adapt to the environment in which the person is moving. Are they going upstairs? Are they going downstairs? Are they turning a corner? Are they in the grocery store? Where are they? Or they don't adapt to the progression of the disease. And motor neuron disease progresses rapidly. So ideally, we want something that can tackle all of these. And so exoskeletons. And we're not the first to think about using exoskeletons in motor neuron disease. There's one other study that I know of from a Japanese group in 2018. They used a really different device. This is called the HAL system. It's a hybrid assistive limb. It weighs 23 kilos, and it's really a rehabilitation rehabilitation tool. So you'd go to a clinic and you'd suit up in this device, which takes a substantial amount of time, and then you would try and get some movement through your limbs. Now, what we're really interested in doing is using tools or exoskeletons that are much more applicable to the real world, that people might actually wear in their daily life. And so we've partnered with this company, Biomodem, that initially developed these devices for children with cerebral palsy. And so what they do is they have this waist pack, they have these cables that run down the side of your leg, and then they have essentially two little motors on your left and your right ankle joints. And they're portable. And essentially what we hope to do is to use them to assist movement and to slow the decline of gait. They're the first device of their kind in Australia, the first globally to be used in MND. And how they work, I won't spend a lot of time here, but I'm happy to chat to you later, is they have sensors under the feet. We call these pressure sensors, and they know when a person their foot is coming down onto the ground. They know how long their steps are. They measure every step, and they know when to provide assistance. You essentially typically want assistance after your foot is already on the ground. You don't want assistance before you hit the ground. And you can tune that level of assistance to be either high or low. So in other words, if somebody, is feeling really fatigued and really weak that day, you can dial up the assistance. If they're feeling quite strong, you can dial down the assistance. They also provide assistance in both directions. So to keep your toes up, but also to push you forward, which is fantastic. And the amount of assistance, like I said, can be user specified. And I have to tell you just a quick little story about my first time interacting with a patient who had just walked in these devices. And because I've spent most of my career at the discovery end of science, not interacting hugely with patients, and specifically not with people who might not live for another 12 months. And I came down to the lab, and this fellow had been walking in the devices for maybe 15 minutes. And I said, "Do you want to take a stroll outside?" And he said, yeah, I really want to go outside. We go outside. He starts walking up a ramp, and then he stops, and then he starts walking, and he stops. And he said, "Taylor, I reached for the wall, but I realized I didn't need to grab the wall. This is the first time in 18 months that I feel like I can walk without needing to hold on to something." At this point, I basically had to leave the room because I was in tears. But the point I want to make is that when you can have a real world impact, an immediate impact on somebody's life with science, it really lights a fire under your tush. Anyway, so what do these devices now look like when people use them? So here's an individual walking in the lab. Again, this person has quite a high deficit. They typically walk in a wheelchair, so they're using the bar. They're learning to use the device here. You can see they're doing a lot of toe pointing, going into a lot of plantar flexion. They come back and we try and reduce the amount of plantar flexion. This is one individual who is able to walk substantially faster and for much longer using the devices. And then, of course, we try and take them outside and see. We have a little track around UQ, and we measure the time it takes people and the number of times they need to stop while wearing these devices. And so we've tested these in about 25 individuals so far. And what we've learned is that when walking in the devices, they're able to walk at faster speeds and they take longer steps, which is great. The little bit of science is they exert more force on the ground. So when we look at their peak braking and their peak propulsive forces while wearing the device, they're higher. And remember Newton's laws. So if you can exert more force on the ground's going to push back harder. And so moving becomes faster, and it also becomes much more efficient. But movement improvements occur outside the lab too. So when we take them along around this track at UQ, we find they walk faster. They walk, they have less toe clearance events, so they don't trip their foot as many times, and they don't hold on to objects nearly as much. And when we ask them, would they wear these devices again in their daily life, majority of them say yes. And they say things like, "I've got an electric wheelchair that I really use for stamina and just for a place to sit down. And I think that with devices like the Spark, I wouldn't need my wheelchair as often. I probably wouldn't need that type of wheelchair." Another said he was feeling confidence within seconds, and felt like they could walk much quicker. And so if anyone has been watching the news this week, the future of exoskeletons is really upon us. So ABC published this article earlier this week about exoskeletons in the workplace, really offering promise to enabling workers to be more efficient, potentially less prone to injury, and have a greater work lifespan. highlighting they won't take people's jobs. They're there to augment them and help them get better. And then Nike had a huge announcement that they're developing world's first powered footwear system. So, and their marketing is very clever, akin to how electric bikes have made it easier to ride farther and more frequently, revolutionizing urban commuting. Nike is developing Project Amplify to make slower running, jogging, and walking easier and more fun. So they're really targeting these devices to make exercise more enjoyable, and so I think they're really going to change the way we work, live, or play, and we're excited to be at the forefront. And the last few slides I just want to tackle are sort of moving beyond humans. And this is an aspect of my research that, I think humans are not always the model system. And when we're thinking about designing devices, we need to be thinking about leveraging biological strategies that animals in nature have evolved over millions of years to move efficiently. And, the movement strategies of animals have already inspired advances in autonomous robots. Some of you are probably familiar with Big Dog and the various Boston Dynamics robots. But their potential to advance wearable assistive devices for humans remains largely untapped. And this is important because humans have a relatively poor gas mileage. So every step we take costs energy, and we choose movement patterns that minimize this energy cost. And you see this bowl labeled walking. When all of you walked here, unless you were running late, you probably walked at a speed and a step length that made you sit in the bottom of that bowl. Everyone has a preferred walking speed and a step length. And if I measured every one of you in this lab, about 80 to 90% of you would choose a preferred speed that minimizes the amount of energy you use. But when we compare a 60-kilogram human or any human to a quadruped in nature, we use about twice as much energy to move. So we're not really efficient in comparison to other animals, and our efficiency substantially decreases as we age. And so what we're doing is turning to Australia's most iconic animal, the kangaroo. And I think we can do a little bit better than these Kanga boots, which I don't think anyone would ever wear. And the reason why kangaroo locomotion has intrigued biomechanists for years is this. So as kangaroos hop faster, so some of you might know kangaroos often use their tail. We call this pentapedal locomotion. If they go faster using their tail, they consume more energy. This line rises. But if they start hopping, they can hop faster and faster without consuming more energy. Humans and other quadrupedal animals have this linear increase in energy as we walk. And so this energetic phenomena has puzzled researchers for years. So we've been building musculoskeletal models of kangaroos, asking them to hop over our force plates, which is a bit harder than humans, and then studying how they move in the wild using accelerometer-based devices. And the goal really here is to try and use this inspiration to feed back into our devices to further improve human efficiency. So if you take-home messages, I think wearable robotic devices like exoskeletons are in their infancy in Australia, particularly, with really exciting potential to restore movement in a range of people with neuromuscular diseases. And I think in the very near future, we'll see these devices more present in healthcare, in the workplace, and even in our daily life. And my sort of call to action, I was asked if I wanted to, is really at this time in Australian science is for those non-scientists to advocate for and support curiosity-driven research. I think discovery, translation and application don't happen without discovery, and we really need to be supporting discovery research such that this application and translation can continue. And of course, we're always on the hunt for Australian-based partners in industry to collaborate with, particularly in this exoskeleton space where it's brand new. And I'll just highlight that UQ recently opened the Center for Motor Neuron Disease Research, and actually earlier today we had Fight MND visit because I think UQ researchers just won about $5 million in grants, not me, but if you're interested in talking more about how to partner, please come have a chat. And of course, research doesn't happen in silos, and I'm really fortunate to work with a fantastic team of researchers around me. So I think I may have gone over time, but I'm happy for any questions.
Thank you so much, Taylor. Yeah, we'll just open up the floor for any questions, and a reminder to our guests online, you can also submit your questions on Slido.
So you mentioned that the main focus of the exoskeletons is for the motor neuron disease. I was wondering too, so in areas, say, like with stroke, where people lose their ability, would these exoskeletons would they be beneficial to these patients as well?
Absolutely. So the first study I ever did in my postdoc was on post-stroke individuals. And motor neuron disease is a little bit different than all the other neuromuscular diseases because your target is not to regain function. They're going to lose function over time. But with post-stroke, one of the big intentions is, to retrain that part of the brain to be able to activate those muscles in a way that allows you to be more symmetrical. And one of the interesting things about we studied this in many young people who'd had stroke, like people in their 30s and 40s. And if you ask them why they choose to move the way they do, they want to look as normal as possible. So they don't care about moving around in a way that's efficient. They care about moving around in a way that looks normal. And if you ask a kid with cerebral palsy, they want to keep up with their kids or their friends at school. So I think how we optimize these devices, like the brain of the device, the controller, really needs to consider what a person's intention about the way they're moving is. But yeah, great question.
Thank you for that talk. I just wanted to understand. I understand that the scope of this lecture is, I guess, restricted to motor neuron diseases and healthcare industry for now. But then, would this also be exploring in the future, say, other methods of movement, such as swimming or flying, things that we also see on the TV? Also, if you can extend this to other things, such as like if people have strokes or are paralyzed, they could also hover because they cannot use any, let's say they don't have any movement as such. So they could use other ways of movement, such as swimming, flying, or hovering to move around. So would that be feasible? Or is there any research being conducted?
Maybe not within my research lifetime, but yes. I mean, one of the big challenges is like the degrees of freedom at your ankle and your knee and your hip are very different than the degrees of freedom in your upper limb. So I tend to stay away from upper limb exoskeletons because the arms and the shoulders are way too complicated for me. If we want to, for example, model every single muscle and how the brain's controlling it, which is one of the things that we do. I foresee, if you look at some of the work coming out of Harvard and the labs there that partner with Boston Dynamics, they're building all sorts of devices to augment the way humans move. And I think the fact that we're seeing companies like Nike and whatnot start to tap into devices, we will see, more devices that can augment movement in a variety of different ways. It becomes a little bit different when you're interacting with water or flying, but yeah, absolutely.
From online, how long does the leg exoskeleton battery last before recharging?
This person's clever. Batteries are the bane of our existence. So that you want to minimize mass because if you add more mass to a person, movement costs go up, right? And so right now we're working with batteries that have about an hour life, but batteries are getting smaller, and so yes, it's a limiting factor, absolutely.
And one more question. What advice would you give to students or early career researchers who want to work at the intersection of science, engineering, and healthcare?
Don't listen to what other people tell you, that you have to choose one, I guess. No, I think one of the keys to being able to work across multiple domains is having collaborators who, really focus in those different domains, whether it be like Derek and Shu. They've spent their entire career studying motor neuron disease. I've been studying motor neuron disease for 3 years and, kangaroos for 3 years. But I think if you can tie the threads together and continuously do things that, keep you passionate and interested, that's what perhaps matters most, because we spend a lot of time as scientists working and thinking about science. So it's got to be things that you're super passionate about.
It's my pleasure to introduce our next speaker, Professor Tim Miller. Professor Tim Miller is the TIEQ UQ Chair of Data Science and Professor of Artificial Intelligence at University of Queensland, School of Electrical Engineering and Computer Science. His work centers on integrating artificial intelligence into decision-making processes to help professionals and organizations make better decisions and improve outcome. Drawing on fields such as machine learning, enforcement learning, AI planning, interaction design, and cognitive science, Professor Miller's research span area include explainable AI, human AI collaborative planning, and human-centric decision support. Before joining UQ, Professor Miller was a faculty member at the University of Melbourne, where he was the founding co-director of Center for AI and Digital Ethics. This background highlights his commitment to ethical and human-centric application of AI in society. Now at UQ, he continues to lead cutting-edge research, enhance efficiency and effectiveness in professional setting. He has described his mission as to improve the capabilities of expert decision maker by using artificial intelligence to do the hard things. Underscore his focus on empowering human experts rather than replacing them. We are honored to have Professor Miller share his insight with us at this alumni event. Please join me welcoming Professor Tim Miller.
Thank you. So, artificial intelligence. My research mission is to help experts make better decisions by getting AI to do the hard things. And so if you've been playing around with AI tools, you think, Tim, you've got a really easy job. These tools are just getting better and better. Well, it's actually not really the case. So over the last 5 years, my lab at the University of Melbourne and other labs around the world have been running a lot of studies at how people can use AI tools to improve decision making. And we consistently find one thing: they don't help at all. They very, very rarely improve the decisions that people make. And in fact, it's worse than that, because what actually happens is people think they're making better decisions with these tools, so they use them, but actually the decisions aren't better at all. And this doesn't just go with decision making. We're seeing this with other generative tools now, generative AI tools like chatbots, such as ChatGPT, where people claim, for example, in computer programming, they're able to program faster and better with these tools. But studies coming out in the last few months show actually they program a little bit slower with a little bit lower quality than if they don't use the tools at all. This is an alarming finding that we can explain with looking at cognition and cognitive science by basically showing that, well, when people are doing something that's easy, they think that time passes a lot faster than when they're doing something that's hard. So when they're engaged in a hard task and doing it themselves, it feels like they're taking a lot longer. But nonetheless, this is a big problem for us. In my lab, we combine cognitive science and cognitive psychology with machine learning and human-computer interaction to study this problem. And what we really look at is the way and the mechanism that people can use these tools in order to improve their decision-making. And so to give you a little bit of an idea of what the field of artificial intelligence looks like is typically when we say, here's a decision that's hard, and we want to improve the decision-making. People get this wrong a lot. Let's try and improve it. What we do is we take a whole lot of data based on past decisions, and we train a machine learning model to make those same decisions. And what I think most people who study machine learning measure is one thing: how good are those decisions? How accurate are those decisions? How accurate is diagnosis? How accurate is it at finding a cybersecurity breach? How accurate? And we can see that these models are getting better and better and better and more accurate. What my lab does is we measure the accuracy of our models as well, but we measure other things. We measure, is it useful for people do they make better decisions? Do they trust the tools properly? Do they trust them? Do they understand them? Does it erode their decision-making abilities if they use these tools over time? And we find that when you start measuring these variables, it changes the type of tools that you have to build. And the state-of-the-art tools that we're building in this case, in other labs now, aren't quite fitting the bill for decision support. Okay, so let's step back and see, how did we get to this place? And so, as I said at the start, it started off with artificial intelligence, machine learning for a long time was, let's replicate the decisions that people have been making. And that actually works really well when you're trying to automate tasks. And there are a lot of tasks that we're quite happy as human beings to automate. Like, for example, the ads that you get shown on social media is an automated thing, and we don't really care whether a human has any oversight on that. But it turns out there's a subset of decisions that we want human oversight in. Healthcare is one, policy making. These types of things we want human oversight, but we can see the value in giving people tools to make better decisions. And so what we thought was, well, okay, there's some in probably the 1980s. Well, here's some tools that we can automate stuff. That's really great. And there's still a lot of them around. Okay, but what about if we want to help an expert decision maker make a better decision? Surely we can take one of these tools, tell them what the AI tool says, and if they're wrong, they'll change their mind. Well, it turns out it doesn't really work like that. People just ignored those tools because, well, you know, you disagree with me. I'm the expert here. Who are you to tell me that you're right? I don't know anything about this. So they kind of discarded those tools and it never worked. And so we had a whole sort of a body of work on trust in this area. And techniques like, well, the tool will give it a recommendation for a diagnosis and it'll explain why. And that will build people's trust, and then they're more likely to adopt the tool. And if they disagree, they can look at the explanation why and figure out if the tool's right or wrong. And I worked on this for about 5 years at the University of Melbourne, and we found something quite interesting, which is that those explanations don't really help people very much at all. Some of my postdocs observed people in a lab making decisions, expert decision makers making decisions. And what we saw was behavior like this. The human decision maker will make their own decision instinctively. They usually have a lot of tacit knowledge. They're very good. They'll make a decision. And then they'll look at the decision support tool. And if it agrees with them, fantastic, they move on. They don't really care if they disagree. When they disagreed, sorry about that. When they disagreed with the tool, we found that they kind of looked at the explanation, they studied it a little bit, they thought for a little bit, and sometimes they changed their mind and they switched to what the tool did, and sometimes they didn't. So we were changing their behavior, but what we found was sometimes they would switch their mind and they were right the first time, they should have just stayed with it, and sometimes they didn't switch their mind and they should have because they were wrong in the first place. And these explanation tools, it turns out it wasn't very good for people navigating, should I trust myself or should I trust the machine? It just didn't help them do that. And so we were observing this, and I read a lot of cognitive science and cognitive psychology, and I was reading some stuff, and I came up with this parable that I'm going to basically give you now. Okay, so this is the audience participation. Sorry, those of you at home, you don't get to participate. So I want you to imagine for a second that you have a pretty tough decision to make it work. It's a challenging decision, you really want to get it right. So put that in your mind, put that in your mind now. And you have a colleague that sits in the office to the right of you and a colleague that sits in the office to the left, and they're both there and you want to go and ask some advice. You only have time to get advice from one of them. You can go right to your colleague, and his name's Bluster. And you can ask Bluster what you should do in this situation. And what Bluster does is tells you what you should do and even tells you why that's a good idea. But if you disagree with Bluster, he says outright, no, this is the right decision. We're going to go with this. He's a very good decision maker, so you probably should adapt his decision. To the left, we have another person who's an equally good decision maker, and her name is Prudence. When you go and ask Prudence, what should I do? What Prudence says is, well, what do you think you should do? And you say, well, I think I should take option A. Prudence says, here's the reasons why that's a good idea, and here's the reasons why that's probably not, also that could be a bad idea. And if that prompts you to reflect and change your mind to option B, Prudence will say, here's the reason B is a good idea, and here's the reason why B is not such a good idea. So I want to have a show of hands here about which one of those two people you would pick if you had a difficult decision to make at work. Who would pick Bluster on the right? One person. Two people. Who would pick Prudence? Okay. So for those of you who can't see on the camera here, an overwhelming majority of people pick Prudence. I knew we were going to do that because I've done this parable many times in audiences in computer science. Why did you pick Bluster? Sarah at the front here.
All you talk for, it sounded like they're probably dealing with. I think
Okay.
people are kind of
Thank you. Thanks, Yeshua.
sort of a Dunning-Kruger thing going on there. People don't know what they don't know, so they just make the decisions on what they think they do know. So I'd rather just go to somebody who knows all the variables.
Somebody who knows what they're talking about and go for it. Good. And you picked Bluster. Why did you pick Bluster?
Yeah, just a definitive answer. Like
Definitive
yeah.
answer. So, okay, so you like the answer. Who wants to say why they picked prudence? There was a lot of you. Anyone want to share? Yeah, thank you, Michael.
Because I don't like to be told what to think.
Yeah. Fantastic. Anyone else want to share there? Yeah, thank you. At the back here.
I think I'd like to have all my options available and then go with this certain, like, based on what the choice, what the scenario is, I can choose the best available option, assess all my options.
Very good. Anyone? One last person want to share theirs down the front here? I'll give you my microphone.
I think by working through the decision yourself, it helps you it helps you understand why you're making the decision you're making, as opposed to just being told this is the best way to do it.
Excellent. Right. So what I can hear here is one thing, control. I like control. I like agency in control. Here I understand what I'm doing. I understand the process here, probably helps in the future. And I like to know I like to explore my option space. Now, if you haven't figured it out already, the reason I give you this parable is to point out something that I point out when I go to computer science conferences here, is when we build decision support, we pretty much give you bluster. That's pretty much all we ever build. We say, train this thing to make the decision, train this thing to make the same diagnosis, train this thing to find the same thing and explain it why. And it fails. It fails repeatedly and repeatedly. What my research has done over the last 3 years is say, well, maybe we should build tools that look more like prudence for some applications. There are some applications where bluster is going to work just fine, but maybe some things should look more like prudence. And I call this, the sort of general term for this is a tool for thought. AI as a tool for thought, a tool that helps you think, not a help that does the thinking for you. That's an old term. It's been around for a long time, but I like it. I think it encapsulates what we use. So let me explain to you a little bit about what tools for thought might look like in practice. Okay, so the first one I'm giving you is an example, is a study we're about to run in dermatology. So since I've been at UQ, I've been working with the chair of dermatology, and over the last 1.5 years, we've run a basic study of a prudence-like tool that improved decision-making a tiny bit, but improved clinical satisfaction inherently a lot. And now we're going to run a much larger study with dermatologists around the world. And so what you might think of, well, if you're trying to get a dermatologist to identify skin cancer from an image of a lesion using a dermoscope, the natural way to do it is to say, well, we'll give a machine learning algorithm that image, and it will highlight for us whether it's a melanoma or a basal cell carcinoma or just a benign lesion. And then maybe we can kind of highlight the regions of the image that the algorithm was looking at, and they'll make better decisions. That's the natural way that you would look at it. And I would argue that kind of fails. It pretty much, we've seen in studies, it improves dermatological decision-making a tiny bit. But dermatologists make a lot of mistakes in diagnosis, and they disagree a lot on diagnosis. So we're trying to push this up. So our tool for thought looks something different. So we're working in a situation called virtual dermatology. So if you've ever been to a virtual dermatologist, you go in and a non-dermatologist called a melanographer checks all the moles on your body, and they're trained to look for moles that look somewhat suspicious. They take a photo of it using a special tool, and this gets sent off, and the next day or something, a dermatologist looks at the 12, 20 images on your body. Now, dermatologists, if you've ever watched them in action, they're really fast. If you ever go and get your moles checked by even a skin cancer doctor, they just look at every image and they can make a decision in under 2 seconds for most of these things. So our view is AI tool support for that's probably a waste of time. Those are easy decisions and they don't get them wrong. Sometimes they make decisions wrong. So what we actually do is we get the dermatologist to go through and make all the decisions themselves, the 20 decisions on your body. And at the end, they say, submit these 20 decisions. And our tool goes through and analyzes all 20 of them and then says, we disagree on 3. Our machine learning model disagrees on 3 of these diagnoses. And when you click on those, it says, here's the evidence that we found that shows we think you're wrong. Now reflect on your decision based on our evidence, and you can change your mind if you want. We think that will lead to slight improvement in decision-making, but a much greater improvement to acceptance of these tools into the dermatological society and probably into GPs as well. So that's one area where we think it can happen. You'll have to wait to see what the results are. We don't know what they're going to be either. But you can use AI as a tool for thought when you go home tonight wouldn't work tomorrow. So you might be using chatbots such as ChatGPT, Microsoft Copilot to do things. And I would argue that the best way to use those is as a tool for thought, not as a tool for, say, writing. So, for example, let's say you have to come up with a strategy for something, a strategy document for something, and you've been thinking about it and you've got all the data you need and you need to think down, really sit down and work out that strategy. The default way to do it is to say, okay, ChatGPT, here's all the data I've got, write a strategy for me. That's probably going to write a pretty ordinary looking strategy, no matter how well you prompt it. It's probably not going to work very well. On the other hand, what you could say is, okay, ChatGPT, I have to write a strategy for this particular area here. Here's a bunch of the data that I've got. I want you to apply Roger Martin's Playing to Win framework, which has the 5 steps in it. I want you to ask me the questions that Roger Martin's framework gets to ask you, and I will answer those questions. And based on my answers, I want you to critique what I've said, and I want you to ask me follow-up questions in order to help me think through this idea better. It's remarkably good at doing these types of things. I know because I've constructed a couple of strategic documents using it. I've got all my data, I sat down and compiled and wrote out a strategy for a new master's degree in probably about 90 minutes. I worked back and forth with this tool. And in the end, what I got was a document that was mostly my own words, but with several ideas in it that came from the tool prompting me to think through specific things. They're fairly good at understanding context. So the questions I got back were specifically about master's degrees in artificial intelligence at Australian universities that prompted me to think through, I had never thought about that question myself. You can go home and use those tools as tools for thought tonight. And I encourage you to do so. So that's the kind of studies we're doing now. But in the next few years, we're sort of looking ahead of this idea of a tool for thought. And there's 2 areas that my lab is looking at. One is scale. Tools for thought work reasonably well, but they don't scale. Machine learning models can make decisions really fast. Humans are really slow. And we're trying to balance that tension. So it's very easy to have a tool for thought where the human's in control of the decision-making process, they have the agency, they can explore the options, but we're the rate limiting factor here. It's very easy to scale decisions. You chuck most of them at machine learning models and it can make it very quick, but then the human's out of the loop and they have a whole lot of problems. There might be specific legislative reasons why you can't do that. We try to balance that tension here. How can we have a tool for thought that allows people to make 3 or 4 times as many decisions in a day, which is really helpful in situations like cybersecurity, radiology, where people are overwhelmed by decisions every day and therefore their decision quality drops. The second thing we're interested in is the idea of de-skilling. So it seems pretty clear that automation tools de-skill people. So experts who make decisions every day start using tools, their decision muscle drops down and they become worse at it. Now, this is a big problem because those are the exact skills you need in order to detect whether a machine learning model is making a mistake. And so if you use these tools, not only will you get worse at the model, but your decision-making, the overall decision-making will start getting worse. And we're interested in how can we use scalable tools for thought to mitigate that de-skilling issue here? How can we redesign and use tools differently in order to mitigate that de-skilling? And so my kind of call for action to this case, we're asked to give a call to action is 2 things. Is 1, think about using these tools as a tools for thought yourself, the AI tools as tools for thought yourself, these interactive large-scale chatbots that you can use, not as a tool to do the mindless thinking for you. And 2, if you're in an organization, take heed to the fact that you might feel like you're making faster and better decisions using these decision support tools, but you might actually be making slower and worse decisions. So if you're interested, you can come out and talk to me and I can work through some of these problems with you. So thanks very much for listening and thanks very much for taking part in my little experiment.
Thank you, Professor Kim. Could we have another round of applause for Professor Kim?
Thank you.
For online, you can submit your question via Slido. And for those who are in room, you can raise your hand. I'll bring the mic.
So with in terms of the medical field, so like if say you have a doctor who works in a particular field using a lot of machine learning, and the machine learning comes back with answers that it knows is correct because of the field. If you then has a patient that comes in with a case that is outside of their understanding, because they may have come up with an unconscious bias in support of the machine learning because of previous results. If the then doctor was then to use it with asking a question it had that the doctor wouldn't know either way, as part of the hard decision making, if the machine learning was to then come back with an incorrect answer, but the doctor wouldn't know any different, and as a result giving a incorrect diagnosis, what sort of what would you put in place to sort of reduce those risks?
Yeah, so that's a great question, right? So this is a risk. This is kind of an accountability question. So what happens if a doctor's largely unsure? They have what's called an automation bias towards a machine. They tend to overtrust it because it's very good at making decisions, possibly better than them. If they make a mistake because the machine makes a mistake, how can you mitigate that problem? And so you touched on a really important issue here, which is the idea of the doctor's is not very confident on their own decision. It's actually, in my view, it's quite a rational thing to therefore delegate to a machine. We have machine learning models that can express their own certainty around decisions. So if a machine's highly confident and you're not confident, it's completely rational that you should say, well, I'm going to accept the machine decision. Okay. In a medical situation here, though, I'm not a lawyer, but I know that the clinician is liable for any mistake that gets made, not the model. And so this is the reason we have this whole thing of having human control and decision making, because we have decision makers who know I'm ultimately accountable, so I want to be involved in that decision. And we don't have many mechanisms for doing that, but the one that seems to work is machine learning models that can express how confident they are. So you tend to find that where machine learning models make mistakes are similar-ish to where doctors make mistakes, which is things they haven't seen very much before. And so if they can express, this is basal cell carcinoma, but I'm really not, this is benign, but I'm really not sure, then the doctor will be more critical of that machine. That's the only thing we really have.
Anyone else?
Oh, the back.
Thank you so much. Just adding to that, basically, is there any guidelines by TGA or FDA being introduced right now on AI for patients?
Is there any guidelines?
By TGA, FDA?
Yeah.
Or how far do you think it's going to be implemented? In how many years?
Yeah, so basically software is treated as a medical device. So there's no particular FDA looking at new guidelines, but this is one of these very slow moving fields, right? Regulation. So FDA, these types of things are looking at guidelines. They're approving software-based decision-making tools, but these are all just liability lies with the clinician. There's no real difference. There is one radiology provider in the US who has said they will take financial accountability for any mistakes that are made in a diagnostic tool, but it doesn't seem like the radiologists care much about that because they know that it's their medical license that ultimately is on the board, and they don't think it'll stand up in court, actually.
Anyone else? We have some interesting question online. With AI systems increasingly impacting people's lives, what ethical consideration do you believe are most urgent today in AI design?
What ethical considerations? Is that? What are the ethical considerations people should have?
Ethical considerations.
Yeah, look, there's no secret to these. Every country has their own ethical guidelines. They all look pretty much exactly the same. There's about 250 different ethical guidelines. And so at a high level, there's principles, right? Principles of privacy, principles of non-discrimination, and principles of the main one. And the third one is accountability, which we was talking about. Those are the three main things. And then the sort of more technical ones are on transparency. Do people who have decisions made about them, do they understand where the data came from, how the models are making decisions, how they were trained? Those are the sort of the main ethical principles. The big problem is how do you actually operationalize those? It seems to be a really difficult problem.
Another one, do you think it's possible to have AI system that are both highly accurate and easily explainable? And what advantage are helping achieve that balance?
Yeah, so it's highly accurate and easily explainable. Yes, it's definitely possible. It's quite difficult. I think that some of the systems we have now are quite explainable and people can understand them. They just can't use them to make better decisions yet. That's the thing that we find. So we ran a whole lot of experiments that showed that people can't make better decisions, but they really understand much better how the models are working when we explain them. They just can't use them for better decisions.
Thank you, Professor Kim
Thank
Miller. I'll hand over mic to Nandu.
Thank you, Shubham. Thank you, Tim. So our next presenter is Dr. James Kesby, a behavioral neuroscientist, affiliate research fellow at the Queensland Brain Institute. Dr. Kesby's research focuses on understanding how psychotic disorders such as schizophrenia affect the brain's decision-making systems, essentially how the circuits that guide our choices go awry when these illnesses take hold. And through close collaboration between scientists and clinical teams, he leads a cross-species research program that bridges animal and human studies to uncover the brain mechanisms that shape behavior. The integrated approach is helping reveal new ways to understand, predict, and treat decision-making disruptions seen in psychosis. Dr. Kesby completed both his Bachelor of Science and PhD at the University of Queensland and has built an internationally recognized body of work at the intersection of neuroscience and psychiatry. Please join me in welcoming Dr. James Kesby as he shares how decoding the brain circuitry is driving new insights, potentially new treatments for psychotic disorders. Thank you, Dr. James.
Is that better? Yeah. Lots of education, technical problems. So I'm trying to keep my slides minimal today, but I do have to cover a fair bit of ground. I'm going to talk about mental health and in particular schizophrenia. Right? First of all, it's not done in a silo, as has been mentioned today. It's a lot of people and clinical spaces and basic discovery spaces that lead to this work. It's a big team. In the interest of time, I'm not going to have a big list of them, but I'm going to go through some of the parts of it. And two, some of these practical outcomes that we've seen from the talks today, they just don't really fit something we don't really understand in schizophrenia. So it's a much slower process. And I think I'd harken back to Taylor's fact that in order to have innovation, we need basic research that we don't necessarily have an application for yet. I'm hopefully going to lead you through some of the challenges we face and some of the work we've been doing to try and drive new ways of helping people with this disorder. So I tried to follow the MO of what we wanted to do, challenge and research and other things. So what's the challenge? It's quite simple. This is an extraordinary disorder. And you can see here from a self-portrait of someone suffering from schizophrenia. This is how they consider the disorder affects them. There's voices in their head that are telling them mean things. It's a big fragmented picture. It doesn't look very nice and comfortable. And this is a story for a lot of people with these disorders. It's very scary. And it leads to these really distorted views of reality. And in a nutshell, what is the impact of living with a mental disorder? Different disorders affect us differently. I think we all appreciate that having these disorders makes it harder for us, right? And in terms of schizophrenia, there's a lot of research showing that basically it's the most disabling of these mental health conditions to live with. And I quote by far, right? And it's also one of the most costly. Now, I'm not in economics. The dollars don't really matter so much, but we're talking cost on the family, the individual, the health system, the fact that someone lives most of their life after adolescence having onset, not contributing and reaching their full potential. Right? This hurts us all in a way. All right, so we need to find solutions to this. This here is a group of people with schizophrenia. They're not really two alike. All right, this adds to the ambiguity. Everyone has a slightly different set of symptoms that affect them. They'll have a slightly different prognosis and progression later after onset. How we track that's important. And what we've got to get to is more personalized treatment strategies. And that's what hopefully I'm going to show you that we're moving towards. But there are some symptoms that are common. It's diagnostically, it has to be diagnosed. One is what we call positive symptoms. These are those psychotic symptoms most people are familiar with. Hallucinations, hearing voices that aren't there, seeing things. Delusions, which is a fixed belief in something that just isn't real, that you can't shake it. Thought disorder, a lack of ability to be aware that these problems are associated with an illness and not real. Then we have decreased behaviors, what we call negative symptoms. Decreased motivation, flat affect, the face is very blank, it doesn't show emotion as well as other people, and asociality, and all these things that affect integration in society at large. And then the thing I'm interested in mainly, for a variety of reasons, is cognitive symptoms. These affect a wide variety of domains: working memory, attention, decision-making, which is my favorite one, which I'm going to talk about. So nice, we've had a bit of a prelude to that. And they're largely untreatable, and they're the ones that result in someone not being able to integrate back into society, even if we treat the psychotic symptoms. And I'm going to focus on decision-making today, because I think it's the most important, at least the most useful for us to target first. Now, we do have some treatments. We have antipsychotic medications. They're called antipsychotics for a reason. There has been one new novel approach to antipsychotic treatment that just got approved. That's in my lifetime. The first ones were discovered by serendipity in about 1960. So we've got a long way to go. We also have what we call cognitive remediation, sort of behavioral training to help someone improve their ability to make decisions. And maybe that's a space where this, prudence comes in and helps us out. It has some effect. It helps cognition to some extent, but really these aren't enough at the moment because we don't know who out of these individuals stands to benefit from them. We don't have the capacity to give everyone the full treatment they need. So where does that leave us with the treatments we have? Of all these people, we don't really know who is going to benefit from what. We know that antipsychotics generally help about 40 to 70% of the people who take them, alleviating some of those symptoms. That's a lot of people left who don't see any benefit of these drugs. Cognitive remediation generally improves performance in about a third of people who do it, and only moderately, not huge, all right? So what's this problem? It's because we've got a huge group of people we call schizophrenia, have schizophrenia, but they're all different. They'll need different medications, they'll need different combinations of these things, right? What makes it even more complicated is that once someone has an onset of a psychotic episode and gets diagnosed with schizophrenia, it's not, here's the problems you have for the rest of your life. It changes over time. We know that symptoms ebb and flow day to day, year to year. Cognition can deteriorate in some individuals. And it's this deterioration in cognition that drives the declines in people's lives. Their ability to maintain work, for example. And if you think this is a disorder that affects people generally around adolescence and young adulthood, when we're going to uni, trying to forge a career, be successful, some of us might have a road like this. Sometimes bends, you can't see very far at some bits, but you know where you're going. Whereas when we think of someone with schizophrenia with these cognitive problems, it's a harder road to travel. Right? It makes it harder to get back into the workforce. We need to find ways to stop this as soon as we can and get them back on the straight and narrow. We've done some research looking at if we would develop things that help in this space, would clinicians even adopt them? Are they aware of these problems? I admire clinicians and I work with a lot of them, but sometimes they're not fit with the literature and what we know. And we've surveyed about hundreds of psychiatrists, mostly in Brisbane, and shown that they are aware, right? So when they rank which symptom group is their priority for treatment, it's positive symptoms, right? The psychotic symptoms. People come to them because they experience psychosis. That makes sense. What we're really interested to see is that which of the symptom groups best predicts the outcome for the individual. It's cognitive symptoms, something they don't really know how to treat. They're not confident in treating, and they're not even confident in identifying the problems in the person. So there's a space here to help clinicians out with their decision-making, but they lack the tools to actually predict and personalize these treatment strategies. And that's what we're hoping to get into and help with. So I'm going to sort of make the case for decision-making in schizophrenia as a road to personalization of treatment. I'm going to talk about two different types of decision-making. Goal-directed action. Sounds pretty complex, but it's not. How do we adapt our choices when reward outcomes change? We have to act to get a reward, and we might have multiple choices. If one reward becomes less likely or less large, not as valuable, we change our actions to go back to the one that's more valuable, right? We can test this using computers at a table. We could set someone up and test you right here. And what we see is that when one value becomes less valuable, one outcome becomes less valuable, people will bias their decision-making towards the valued outcome here in blue, all right? And we can show this at different ages across multiple studies. Pretty straightforward. When we look at people with early psychosis at the very initial stages of this disorder, they can also do that fine. Right? But when we look at people who've had more chronic disorders, we see that there's a huge proportion of people with persistent psychosis that fail to adjust to that change. Even though when we've tested them, they're aware that it's not as valuable. One of those options is not as valuable. They don't bias their responding. Right? And about 60% we find have a problem. So there's this deterioration in a subgroup of people that progresses over time. The other task I like to do, and this is much more complex, I'm going to give you a very brief overview of it. It's called reversal learning. And essentially, how can we rapidly update what we know about the world and change our response and adapt? Flexibly going back and forth between two different options as they change. We do hundreds of trials to test people with this. And we look at a few things. One is how someone responds to a reward or how someone responds to a loss. And here, what we're looking at is an early psychosis in pink versus age-matched controls. How often do you select something the same again after you've been rewarded for it? Pretty often for most people, right? No difference between the groups. Makes sense. If you get rewarded for something, you do it again, right? Pretty simple. Yet, after a loss, people with early psychosis are less likely to change their choice. So they're more likely to pick that same thing again, even though they didn't get a reward. This looks a bit different when we go longer into the disorder. When we look at persistent psychosis, we see a deficit in their following after all, making that same choice again. And this has been shown in the literature in a variety of scenarios, what we know, right? No change in loss. So here we have another thing where we have this phenotype early on that changes and progresses, right? But we're really interested in what causes this switch, because a lot of cognitive mediation tasks and tools and trainings about learning about reward. What if it's not going to be effective in early psychosis? Because they're responding to reward correctly. I'm interested in the brain. If we want to get new treatments, we need to know what areas of the brain we're targeting, which neurotransmitters are contributing to it. So we use model systems to test some of these theories as to how can we make a mouse look like a person, decision-making wise, with schizophrenia. So a little bit of work in a very summary level of what we've done. Looking at this goal-directed behavior, if we manipulate dopamine systems to mimic psychosis, you have a drug that increases dopamine in your brain, you are more likely to have a psychotic episode, right? So we can give dopamine-enhancing agents to mice. And we see that when we look at goal-directed behavior, our control mice, they bias their actions towards the value live, just like a human would, all right? They're pretty good at this stuff. When we increase dopamine systems in the brain, they don't do that anymore, not significantly so. They're less able to make that same choice, the same as we see in someone with schizophrenia. So increased dopamine function in this task shows the similar results to what we see in people with persistent psychosis. What about reversal learning? Here we see something a bit different. When we increase dopamine the same sort of way, we see no changes in the reward, but we see this decrease in the response to loss. These are normalized slightly differently because of the way we do the task. Nevertheless, you see that same decrease. Similar to what we saw with early psychosis, they're sticking with the same choice after a loss or optimization. When we decrease glutamate, a different transmitter, and inhibit some function in certain systems, we can now mimic what we see in persistent psychosis, a decrease in response to reward, no effect on loss. So we're looking at this shift from loss to reward, and it could be different neurotransmitter systems that drive that. And obviously there's more nuance to that, but what's really cool is that this shows that there's a progressive neurobiology, a shift in actually the neurochemistry underlying the disorder that might drive some of the cognitive effects we see. Neurochemistry is important. That's what our drugs target. And what I think is most exciting about this is that progression sounds bad, deterioration sounds bad. It is, but it's also a window of opportunity to prevent and stop that decline. So we have our people. What we're looking at is early psychosis has this loss-based phenotype that progresses to these reward-based problems. In our mice, we tinker with dopamine systems. We can mimic some of this early, but also if you have long enough on dopamine, you can impair some of these more reward-based processes. And what we're looking at is an increase in striatal, one area of the brain which we associate with psychosis. This is increased function. It's a hyperactivation early on in the disorder, potentially. Yet to mimic what we see in persistent psychosis, we actually have to decrease its function and alter glutamatergic systems. So there's this shift from hyperactivity, that early stage of the disorder, that maybe starts to impair the whole system and it falls apart later on. And we've prefaced this as a kind of a different hypothesis to what people have described, because people are either dopamine or glutamate in this disorder, right? Most of our drugs target dopamine. What we think is happening is actually progressive hyperstimulation of these systems by dopamine could lead to more broad cognitive dysfunction. And that allows us a place to go and hopefully help them. So where do we stand with our group of people with schizophrenia that all have different symptoms, potentially need different interventions? I said there's a window of opportunity, right? But each person needs to look through a different window to see the outcome that's going to work for them. Some people might need just our typical antipsychotics we have now, and they're going to be okay. They're resilient. We see lots of people go back to work and they're very high functioning. They're on a dose that works. They can manage that for the rest of their lives. There's evidence in Australia that suggests some people might be just as well going through cognitive remediation and actually not taking any antipsychotic treatment. There's a lot of side effects with these drugs. You don't have to take them. You don't want to take them. Conversely, the combination of both is what's probably recommended worldwide. You should get cognitive remediation. when you've been treated for these psychotic episodes. We don't have the capacity in the health system to do that, but we should. And obviously, finally, the development of new targets, targeted drugs based on the neurobiology of the disorder. We still don't know how to get this person to the right window. Our prediction of who develops schizophrenia is pretty tragic. Even if you come seeking help with sub-threshold psychotic symptoms, we do all the best surveys that Australia has developed over the last few years. About a 1 in 10 chance of predicting if you get schizophrenia. So we can't do much up until the early psychotic episode, but we can use some of these switches in behavior to start predicting who is most likely to develop these problems. And that's why I'm optimistic. And I use that term because we've got a study we're going to start called Optimism, which is actually going to address these things. I said I'm interested in the switch between that early and late phenotype. They were different people. We recruited people who had persistent psychosis and people who had early psychosis. So we can't tell who ends up where. That's the next step. And it's a big mouthful, so I won't go through it, but it highlights the point. We're trying to find ways to inform symptom management, give clinicians an easier time of directing people so that the right people go to the cognitive mediation versus get different drugs. And the idea is to identify which of these cognitive traits, which of these loss responses actually allow us to predict a decline in cognitive function. Because what we found actually is that the change in loss responding actually was less clinically severe individuals. So it might be a compensatory mechanism dealing with this hyperflux of dopamine. And that means they're resilient. We don't know yet. So we're following up early psychosis, people with early psychosis over 2 years to track their decision-making over time. See how that influences the response to cognitive mediation and what decision-making outcomes we can predict early on. Most people in the early psychosis teams and clinicians, they get a few sessions with a person before they send them back to the care team. The moment they're looking at psychotic symptoms and using the drugs they have, we want to give them some tools to actually help them push people in the right direction as early as possible. So the idea is to develop a simple screening tool that clinicians can use in their own lab. Because if you want to get cognitive testing, you go send it to a neuropsychologist, they'll get you a result in probably 2 months, and he'll say, cognition is okay. It's not very good. It's useful if they're very impaired and you've got to send them to the justice system or something. We're going to develop one that's a tablet in the clinic that can be administered at the last session that the psychiatrist sees them. They've managed their positive symptoms. Now we're going to say this person is likely to be okay, be resilient, send to normal care, normal teamwork as possible. The other one we think has a problem, maybe declines, and would probably benefit from cognitive mediation. So the 1 in 4 people that they refer to cognitive mediation becomes the correct one. And that's the goal, and it's still a way away, but that's where we're moving towards. And obviously it's not done without the funding we have, and a special shout out to UQ Young Alumni Board who's sponsoring our Optimism project as well through their party of purpose. So I'm happy to answer any questions. It's a lot of overview because it's all very nuanced, but yeah, thanks for listening.
See, it's working now. Thank you so much, Dr. James, for your insights and also all the work you do in this industry. Any questions on the floor?
So in your presentation, you mentioned about how increasing dopamine can bring on a psychosis episode. Is there a way to reduce dopamine in the brain that might reduce those levels, and then cognitive mediation might, would that have a greater impact if the dopamine levels are lower?
Yeah, good question. Generally, the problem is that the increase in dopamine is not consistent across the brain. So the nuance is that we have an area of the brain called the striatum. Most of that dopamine is there. It has very different functions, and it's only one little part of that where the hyperfunction leads to psychosis. When you take a drug, it impacts everywhere, but really in schizophrenia, it's one area. When you decrease dopamine, you get negative outcomes as well. Your reward anticipation, your motivation to do things, that drive is a dopaminergic response. And if you block that, some of the problems associated with depression is a dampening of dopamine. We also know that cortical dopamine systems, if you block them, you impair working memory further. So it's, yeah, and so Parkinson's, for example, is a degenerative disorder of dopamine system. So you get motor problems if you knock out too much. So finding a way to manipulate dopamine systems in just that one area is the trick. And there might be some different neurochemistry in there that we can target at some point, and that's what the preclinical work is trying to find out. How can we make sure that what we impact is just in that area? So yeah, the long goal would be to somehow manage that dopamine. At the moment, we're just blocking the signaling side of it, so we're not even fixing the problem with things. Yeah.
Any other questions? We have some questions online. Is there a connection between our quest for dopamine through social media and potential psychosis or schizophrenia? Are children more prone to damage than adults?
I get asked this too often. Yeah, everyone's familiar with dopamine being this pleasure chemical. It's not a pleasure chemical at all. It is something that helps us act. And yes, things like social media, pokie machines abuse that system to keep us doing something that might not be beneficial to us. I don't think there's been enough research on too much social media at a period of time. We do know that there's a variety of environmental effects that can impact your risk. If you have stress and you're less social during the key period of your adolescence, that increases your risk, right? Now, one might argue that being on more social media leads to more social stress and less actual interaction with people. And if you're already vulnerable, then that could lead to an onset, and it might lead to recreational drug use, which is another thing. So yeah, that while the systems aren't that inclined, I wouldn't be able to say yay or nay for that, but they do try to play on our dopaminergic system, that normal reinforcement. Yeah.
On the whole decision making, yeah. Another thing is, what excites you most about the future of brain research? Are there any emerging technologies or collaborations?
Good question. So in the world of neuroscience, like the auxiliary machinery and all the metals that are being developed, we have heaps of cool new tools, and they're really good. I said that the dopaminergic change in schizophrenia was one small area. 20 years ago, we thought it was a different area because all we saw was a big blob when we measured things in the brain of living people. The cameras, the radioisotopes we use got better, and then everyone went, hold on, it's not there, it's here. So just like a better camera basically revolutionized what we think of with this disorder. So they're constantly coming forward. And in terms of new collaborations, I think I'm working with some people in Brisbane now that are very interested in how we integrate cognitive mediation. And in terms of, aside from developing new treatments, using the ones we have more effectively, I think is the best way we can help at this point in time. So integrating cognitive mediation services better is something that I think is going to have the biggest impact in the short term.
Thank you for that, Dr. James. It makes sense. So that's all the time we have for questions. And thank you again, Dr. James, for sharing your insights and, sharing us the research. And you would have seen Dr. James if you attended Party with a Purpose, which, the Young Alumni Board organizes every year. So keen to see you next year. And thank you to all the presenters for, presenting today. Next, I'll, yeah. I'll hand over to Janita.
Thank you, Nandu. He did already thank all of you, though, which is what I'm going to do as well. But thank you, everyone, so much for coming tonight, and thank you to our brilliant, brilliant speakers tonight. Going back to what I was saying at the beginning, the Beyond the Boundaries, the newest discovery shaping your future is what I was trying to say, and I think that we can all agree that. I think that we can all agree that that is exactly what we did here tonight. We do have a small token of our appreciation to the speakers for tonight. So just a little small gesture, but thank you so much. A big thank you as well, obviously, to Nina Gardner and Maddie on the UQ Advancement team. These events are definitely not possible without them. And of course, thank you to all of you and our guests for joining us online as well. Please do stay for a while. The event is open until 9 p.m. So please stay for a drink and a little bit more food. And I hope to see all of you next year. This is our last event on the Young Professionals portfolio for this year. But we will be back next year with some more great things. Wonderful. Thank you, everyone.